All right. So we run into one of our first problem solves that we're going to do here. Okay, we've talked a little about using conversions to solve problems, but now we're getting into word problems. So I want to introduce word problems because a lot of people look at these and they think, how am I going to solve this? I don't know. I'm going to sit down and I'm going to go watch a couple of seasons of One Tree Hill, right? Okay. So here's a question. Calculate the speed of a helium atom moving at 935 meters per second. Okay, now, how many people here are stumped right off the bat? Okay, good. Now, people are wondering why you're raising your hand in front of a computer. Okay, but at least I'm happy that you're honest. Okay? Don't be ashamed or embarrassed that you can't solve these things. Okay? Because a lot of what you've been learning in high school is mathematics in the abstract, mathematics in a vacuum. Not a lot of applied mathematics when you're dealing with algebra, pre-calculus, and calculus. Okay? The reason being is that things get a little murky when you start transferring mathematics from the abstract into mathematics in applied terms. Okay? In science, there's not a big difference between what you've learned in algebra or calculus and what you're going to be learning in the science. A lot of what happens is that those variables that you're used to seeing, x and y, in calculus or in algebra, those types of things suddenly take on different identities in science. It's just your job to figure out where the x and the y are. So your job is to find out which one of these are variables and what information do I need in order to solve the problem. Okay? So what I'm going to do is I've got a convenient little line here. Right? Now that I've got the convenient line, I'm going to show you how to solve this in the science terms and then how to solve this in the mathematics terms. And if you can get these two things to sort of mesh in your brain, you'll be able to solve these variable problems a lot easier. Okay? So the first thing that we want to do when we're looking at these types of problems is develop a strategy on how to solve it. Okay, you got to identify what the problem is. Okay? Remember the scientific method here. Okay, we have a problem. What's the problem? Got to identify the problem. Then we got to do a hypothesis to figure out how to fix it. So our problem here is we've got to calculate the speed of a helium atom moving at 935 meters per second. So what do we have? We know we have a helium atom, and we know that we have 935 meters per second. Now what is 935 meters per second? Now if you haven't taken physics yet, or you took physics in high school, and your physics was a lot like mine, where we did a lot of auto mechanics, strangely enough. Okay, but I'm just kidding. My physics teacher is actually pretty good. And we did talk about this stuff first semester. 935 meters per second. What is it? That's how fast something's moving, right? Let me put it to you this way. Can you convert this into something that's a little bit more familiar to you? Like miles per hour. Notice that I've got distance up here on the top, and I've got time down on the bottom. In this one, I've got distance and I've got time. Yeah, it's a speed value. So I've got speed here. What's another word for speed? Not methamphetamine. God, I can't believe you just said that. It's velocity, right? Okay, so this is a velocity term. Where have we just seen velocity? Aha, yes, you remember. Energy. I just realized that I made a mistake on the problem. But energy is equal to 1/2 mass times velocity squared. All right? Now, if you are paying attention, you look at this and you say, well, calculate the speed of a helium atom moving at 935 meters per second. Actually, the answer is 935 meters per second. You're right. Sorry. I want to calculate the energy of this thing. My first problem is not starting it off well. So calculate the energy of a helium atom moving at 935 meters per second. So what do I have here? Okay? I want to calculate energy. So my question here, my problem, my identified problem is that I've got to calculate the energy. Calculated energy, right here. E. So I've got to calculate that. So what terms am I given here? I've already identified that this stuff is velocity. And that's v, right? So I've identified what v is. The only thing that I'm missing in order to solve for E is going to be mass. Unfortunately, I've been told what my atom is. And my atom is a helium atom. Okay? And you can look at the mass of a helium atom and find out that the mass of a helium atom is 4.003 AMU. Okay? If I want to convert that, let me move this over a little bit. If I want to convert that into grams, all right, what I'm going to do is then divide this, okay, for 1 AMU, this is the conversion, 1 AMU is going to be equal to 1.661 times 10 to the minus 24 grams. All right? And when I do that, I get 2 grams. Now there's something important that we have to look at this, all right? And energy in these terms, we have to look at how we want to express the energy. The energy that we're going to be using in this term, okay, is a joule. And a joule, so 1 joule is equal to 1 Newton times 1 meter, okay? And 1 Newton is equal to 1 kilogram times meter squared, right? Yep, meter per second squared. Okay. So let me write this down here. 1 joule is equal to 1 Newton times meter, okay? 1 Newton is equal to 1 kilogram times meter per second squared. All right? So I'm going to take the definition for Newton and plug that into that equation. So my joules are equal to 1 kilogram, so I'm just going to write kilogram here, times meter over second squared times meter. So, at this point, just multiply meter into this thing, and what I get is kilogram times meter squared over second squared. All right? So that's the energy value of joule, and that's what we're going to be using in this throughout the semester. And notice that I've got kilograms here. All right? To put that into the correct unit, I have got to transform this from grams into kilograms. So I know that 1 gram is equal to 1,000 kilograms. Right? Does that make sense? How many people are asleep at their computer? This is my test to see if you're asleep. 1 gram, like this pen top, is equal to a ton, a metric ton. Yes? No, of course not. That's crazy talk. But this happens all the time when people are doing their conversions. Pay attention to what you're doing and make sure you go back and check your work. 1,000 grams is equal to 1 kilogram. These cancel out. AMU cancels out. And what I'm going to be able to do is get out how many kilograms 1 atom of helium is going to be. So 1 atom of helium turns out to be, let's see, 1.661 times 10 to the, let's see, multiply that out. And what we get is 6.649 times 10 to the minus 24 grams. And now at this point, I've got mass. Okay? So I've calculated mass at this point. So in doing so, I've got mass, and I've got things in kilograms. Nope, that's kilograms, sorry. So kilograms is equal to mass. I've now solved for F. Now it's just a matter of multiplying the two terms together. So 6.649 times 10 to the minus 24 kilograms times my velocity, which is 935 meters per second. Okay? And my V value has got to be squared, right? So I've got to square that. And notice that I have to square the units as well. If you look at this, meters squared, second squared, that's where that value comes from. All right? And then multiply this by 0.5. Okay? Now the rest of it is working on a calculator. And what I get is 2.906 times 10 to the minus 18 kilograms times meters squared over seconds squared. And another convenient way of looking at this, I can just write joule instead of writing all of that stuff out. All right? So I've calculated the number of joules that this is expressing at this point. Okay? And I told you I'd figure this out using the math components. All right? So let's do it that way. All right? I can look at 1/2 mv squared, okay, is equal to E. Now at this point, I'm going to calculate for E, but I'm going to look at these things and say mass is going to be my x term, and V is going to be my y term. So another way of looking at this in the abstract mathematically is 1/2 xy squared is equal to E. Now in this case, we've got values, so we can solve this 3-variable equation by looking at the values of 2 of the variables. If y is equal to 935, okay, and x, that was the one that was hard to figure out, right? That's our value for x. 6.649, excuse me. Okay, so a very small number times y squared times 1/2, and that'll get us our value. That'll get us our numerical value, but notice I didn't put any units here, because the abstract does not normally include units. That's why it's abstract. When you go to science, you include the units. And then suddenly it becomes applied at that point, because we've got units there. Okay, so the mathematical term of this, all right, if I plug these values in, 6.649 times 10 to the minus 24 times 935 squared, and that's going to give me my E value, a unitless E value, so be careful how you do this. Now, one thing I do want to caution you about is when you get the final answer, you look at that and you say, it's all correct. Why? Because my calculator told me so. Remember, your calculator can't do significant figures. Have I done this correctly with significant figures? How many sig figs do I have here? That's right, 4. 4 sig figs here. All right? How many sig figs do I have there? Another 4. Okay? So far, at the end of this mathematical equation, I should have 4 sig figs out. How many sig figs does this entail? It's a definition. That's right. So that's infinite sig figs. All right, so I've covered the mass part. Let's look at the velocity part. How many sig figs do I have with 935? Yes, 3 sig figs. So how many sig figs should my answer have? If you look at this answer, I've got 4. Even though I put it in scientific notation, which is pretty sweet, I've got too many sig figs here. So the correct answer to this would be this. All right? Always double check your significant figures. Okay.